Okay, today's the first day we're going to talk about an important theorem that we're going to use throughout the year to verify certain cases, and we'll also use it to do some verifications for AP problems, and that's what we're preparing for. So we need to make sure that we are learning this theorem and remembering its parts. So there's three parts to the if, and so we need to remember all three of the if parts. In order for Rolle's theorem to apply, it has to be continuous on the closed interval. It has to be differentiable on the open interval. And f of a has to equal f of b. If any of those three parts are not true, Rolle's theorem does not apply. What Rolle's theorem says is if those three parts are true, then there exists at least one number c where the derivative equals 0. This is going to be much easier to see by looking at these pictures. So first let's test to make sure Rolle's theorem applies in each of these three pictures. The first thing we're supposed to look for is that it's continuous on the closed interval. Notice from A to B it is definitely continuous. I'm not picking up my pencil. I can draw a straight line from point A to point B. Picture 2, also continuous from A to B, and picture 3, continuous from A to B. So all those have the continuity met. The second thing is differentiable on the open interval. Remember, it's not differentiable if it's at corner, cusp, asymptotes, and at endpoints. But since we're talking about open interval, their endpoints are thrown out. Notice there's no corners, cusp, or asymptotes in picture 1, no corners, cusp, or asymptotes in picture 2, and none in picture 3 also. So it does meet the second requirement. The third requirement is that the heights of A and B have to be equal. Notice how the heights, or f of A equals f of B, on each of the three pictures. So the three requirements are met. That means then there exists at least one number c where f prime of c equals 0. So notice it said at least one. This one has just one value of where the derivative equals 0. However, in the second picture I have two cases, two c values where the derivative equals 0. And in picture 3, I have 5 cases where the derivative equals 0. So I have 5 c values. There's a couple of reminders I'll go along and talk about again, and that's polynomials and rational functions and trig functions are well-known differentiable functions on their domain. That's really a key that we're saying on their domain. If it's not part of their domain, well, then we're not talking about that part being differentiable. Also, a reminder is that a differentiable function, if you know a function is differentiable, then it is also continuous. The first example I want to talk about is I want to explain why Rolle's theorem does not apply to this particular problem. So if you remember, if Rolle's theorem is going to apply, it has to meet these three conditions. It has to be continuous, differentiable, and f of A has to equal f of B. So what I would do is tell you to graph this on your graphing calculator, and you could type that in as cosine of x over 2 divided by sine of x over 2. You will get a picture with asymptotes at 0 and at 2 pi, and I believe it looks something along these lines. I have this first one a little off here. But we get the idea, the general idea. We know that these are actually the same. My drawings are just really bad. But why does Rolle's theorem not apply? Well, I see that it's not differentiable on this interval I'm talking about. It's not differentiable and it's not continuous. So there's no way that Rolle's theorem can apply to this. So we'll just say Rolle's does not apply. Rolle's does not apply because the function is not continuous or differentiable on the closed interval pi to 3 pi.